So number 16 here, we have a 20 kilogram sphere, and it's rolling down this inclined plane, and it says it's not slipping. So that's important. When you see that sort of thing, then catch, and we've talked about this a little bit already. Once you see that, that means you can go with the relationship that the acceleration of the object is going to be plus or minus alpha r. Okay, so alpha and a are going to be connected if it's not slipping. So our job now is to find the angular acceleration and the acceleration of the center of mass. Okay, that's cool. Since we've got a is plus or minus alpha r, all we have to do really is find alpha, and then we're in good shape. So let's look at our forces like we generally do. And we're going to have a normal force here. And then we've got weight, which is here. All right, but I want to split it into its components. So I don't really want to draw it that way. I'm going to go ahead and have my parallel component and my perpendicular component. And the parallel component is going to be mg sine theta, and the perpendicular component will be mg cosine theta, just like that. All right. Then we've got some friction in here as well. Okay. Now, how can we figure out what's the direction of the friction? Well, let's suppose that, we know that the perpendicular component of the weight and the normal component cancel each other out. Okay. They're not going to do anything to the motion of the object. So all we have is that parallel component. Suppose that we only had the parallel component. In other words, no friction. If there were no friction, then the ball would actually slide down instead of rolling down. Okay? And if the ball then slid down, all right, we would have mg sine theta is ma. A's are going to cancel, and we see that the acceleration is just g sine theta. Okay. But this ball is rolling, and it's rolling because there is some static friction pointing back this way. Okay. Now, if it were kinetic, then we would know exactly the value, mu mg cosine theta. Okay, mu times the normal force. But it's static, so that means it's variable. So we don't actually know what it is. Okay. And so when we come up and try to think about what's the acceleration down the plane, we could say, well, this is what we've got here. The problem is we don't know F sub s. We don't know that friction, nor do we know the acceleration. Okay. But we've got this relationship here between the acceleration, both accelerations. Okay. So maybe we don't need to calculate the translational acceleration directly. Maybe we can just calculate alpha. So let's take a look at that. And it's going to be best to put alpha here. So when we sum the moments, and let me call that point A, then we get no moment contribution from that frictional force, which we don't know anyway. Okay. So let's turn all these into little sub A's, just like that, and we're going to be good to go. Okay, so no moment from friction, no moment from normal force, no moment from the perpendicular component of the weight. All we have is a moment from the parallel component of the weight. So we've got W parallel, and it's out there at a distance of 0.15. That's IA onto alpha. We do need to find I sub A. Okay. So I for a sphere is 2/5 mr squared, but it's offset. So we have to use the parallel axis theorem. So we've got m Usually I put md squared, but let's just call it mr squared this time, because r is d. So we've seen that a few times. And now we've got our 2/5 mr squared. And when you run the numbers on that with the mass and the radius and all that, what you're going to get is 0.63. Okay. And you should run those numbers. Make sure you get that same answer. It'll be good practice for you to do that real quick. Okay. Calculating those moments of inertia like that needs to be like second nature to you. Just boom, boom, just pop it right out. Okay. Back to trying to find alpha. So if we do a little bit of algebra here, we're going to get 0.15 mg sine theta, because that's what our parallel component of the weight is, divided by IA. And then when you run the numbers on that, plug in, what you're going to get is 23.36 radians per second squared, like so. Okay. All right. Well, now we can use our handy relationship that relates A to, it's going to be plus or minus alpha R. So we got to figure out, is it going to be plus or is it going to be minus? Okay. I guess I didn't explicitly say it, but I called this positive translation, and alpha coming around this way is positive there. So those guys are in line with each other. So a positive alpha turns into a positive translational acceleration. So I can just use plus as I'm going through that. So here then I'm going to have 23.36 times the radius, 0.15. And that means that A turns out to be 3.504. Okay? Meters per second squared. Just like that. Now, what's the effect of the rolling? Okay? Well, we got that the acceleration was that 3.5 number. And we said if it hadn't have slid, then we would have had this number up here. Now, sine of 30 is a half, so that would have been 4.905. Okay, so the fact that it rolled detracted or took away from the translational acceleration. Okay, so if we had greased the surface and let the thing slide down, it actually would have gone faster than it rolling, which is a little counterintuitive. Okay, and hard to do. But if you put a block on little teeny tiny wheels, okay, then the effects of the teeny tiny wheels is minimal and basically doesn't affect. And it's kind of like the block then is just sliding. Okay. And that's what those little green cars we used in lab, that's what there's like. Big, heavy car, teeny tiny little wheels with dinky moments of inertia and very low friction. Okay, it's basically like the block is sliding down. The cars are sliding down the incline. Okay. Now, I want to take a little diversion here and show you something kind of interesting. So every object, when we think about its moment of inertia, has some kind of moment of inertia of the form due to its geometry of beta mr squared. Okay. Beta in this case was 2/5. If it was a disk, it'd be a half. If it was a hollow sphere, it would be, I forget, 4/5 or something like that. Okay. Now, what I want to do is I want to say, let's suppose we just make this some generic shape so that there's some beta that corresponds to its moment of inertia about its center of mass. Okay. So if we're offset, like we were in this problem with some A, then what that means is we could write I sub A as mr squared plus beta mr squared, which is to say we can write the moment of inertia as mr squared 1 plus beta. Okay? So if we do that, watch what happens if I kind of go back to this relationship here. I'm going to have exactly the same equation right here, okay? Except 0.15, remember, is actually the radius of the thing. So let's write down what we get for alpha if we do that. We're going to get that alpha is equal to r mg sine theta, and we divided by mr squared 1 plus beta. And then that turns out to just be the m's are going to cancel. I'm left with an r in the bottom. I'm left with sine theta, g sine theta over r 1 plus beta. Okay. Now, if we take that one step further, that's the angular acceleration, and we look for the translational acceleration, we just end up multiplying times an r. So a is alpha times another r. So we're going to have rg sine theta over r onto 1 plus beta. The r's are going to cancel, and I'm left with g sine theta is 1 plus beta. Okay. And so we could put in beta for 2/5, and we're going to end up getting the acceleration we had before, 3.504. Okay. But it's kind of a cool trick there, and allows us to see what's the effect of different beta values when we do this thing. Okay. And so if we were on campus, if we were in class, I would do a demonstration for you where I take a hoop and a disc and put them side by side. A disc here. Okay, it's a solid disc. And then right next to it, a hollow hoop. And they've got the same mass and they're the same size. But for the disc, the moment of inertia is 1/2 mr squared. Oh, I should do that color appropriate, huh? For the disc, beta is 1/2. But for the hoop, beta is 1. It's just mr squared. Okay. And so what happens when you race these things, so I usually hold them both at the same time, ready, set, go. Okay. Is that you see the disc outpaces the hoop. It outpaces the hoop, and it actually gets to the bottom sooner. And it's a strange result, and it doesn't really make sense until you think about what's happening with the energy of the two objects. And that's what we'll get into in our last block of material for the semester. Okay. All right. So we have hit this one hard. Let's be done with it.